Welcome to the second day of Cascadia. Thanks for being here all bright and early after that awesome party last night. I work at Esri's Portland R&D Center here in Portland, and I would like to thank you for showing up. I'd like to state up front that there will be absolutely zero code in this talk because it's 9:30 in the morning. There will be some math, however, so get prepared for that. The goal of this talk is for everyone to be able to take something away to think on for the future, no matter whether they're an accomplished computer scientist, consider themselves an artist, or whether they look at programming as a craft. So for those of us who have a degree indicating that we have studied the discipline of our careers, that degree probably says computer science. One of the newer scientific fields, the structure and interplay of the computer science department can vary quite differently between different colleges and universities. Computer science was born out of mathematics, but has physical component that formal mathematics lacks. The physical properties that create and control the function of computers also encourage study along many alternate paths, like physics or electrical engineering. Some computer science programs continue the tradition from other science fields of having lab classes, while others are almost entirely theoretical. It is entirely possible to graduate with a degree in computer science without having actually written code that runs on a computer. So if students aren't learning how to code in computer science classes, what exactly are they learning? One of the fundamental classes of any computer science department is the analysis and study of algorithms. Studying algorithms abstractly, that is, devoid of any requirement for a particular programming language, encourage us to divorce the implementation particulars away from the underlying properties of the algorithm. Algorithms are analyzed based on overall complexity, also known as big O notation. What we're trying to determine is how does this algorithm scale? Running an algorithm on a set of 10 items is almost always fast. What happens when that set grows to 1,000 items or 10 million items? So here's a graph showing how algorithm running time increases as the number of elements increase for different big O notation designations. When we're analyzing an algorithm for big O notation, we only care about the highest order factor. We ignore constant factors or any lower order terms. So the best area to be is O log of n. This is the blue line, very bottom. You can barely see it sloping as it grows. Generally, algorithms that run in O log n time are running on sorted data. This is why it's so important for us to create database indexes, cache things, or otherwise pre-sort or pre-organize our data. Order n algorithms are simply linear. They grow equally with the size of the data set. O n log n, which is also known as log linear, this encompasses many of the best sorting algorithms. And we know it's important to be able to sort efficiently so that we can then search in O log n time later. Now we get into some of the trickier areas. Quadratic, which is O n to the squared, or polynomial if that factor is any higher. These are algorithms where you're starting to get into some area of rapid growth. You have to pay a little bit more attention to your implementation. And now we're getting into the danger zone. Exponential, this is O2 to the n. These pretty much require us to know that we're going to be running these algorithms on limited data sets. The exact solution to the traveling salesman problem is an exponential algorithm. And now we get into the area where if you're trying to write an algorithm that's factorial, O n bang, just say no. Just step away slowly from the computer. Do something else. Attempting to solve this traveling salesman problem in a brute force approach is a factorial algorithm. So what exactly is an algorithm? It's a set of instructions that will solve a particular problem. A problem might have many different algorithms that describe correct solutions, and many more that might provide good enough solutions. So I'm going to talk about the convex hull problem. A convex hull is a mathematical term to describe the envelope of a set of n points. And the easiest heuristic for envisioning this is to envision wrapping a string around the set of points. The points on the string touch are the points on the convex hull. And while this picture is quite pretty, they didn't really understand the concept of the convex hull and kind of got a little messy there. But it's more beautiful than anything else I could find, so it stays. It is true that the vertices creating the polygon representing the convex hull consist entirely of points within the set of n points. Yay, mathematics. Convex hull is a mathematical concept that has many real-world use cases, including in computer graphics. Using a convex hull instead of a standard bounding box can give you much more accurate intersection calculations when trying to determine what to display on the screen. It's also used in pattern recognition, image processing, and GIS. Finding the convex hull allows for further calculations, such as finding the centroid or the center of gravity of the polygon, or to, as I mentioned before in computer graphics, allowing for intersection calculations. So first I'm going to talk about the brute force approach to this problem. And this involves iterating through all the different pairs of lines between each pair of points. And you'll notice that I gave up pretty soon after trying to write these lines because even with a small data set of 9 points in this example, the number of lines is quite expansive. So the brute force algorithm takes advantage of the fact that for any line on the convex hull, if you look at all the remaining points, they will all be located on one side of the bisected plane. So this line right here, which is not on the convex hull, has points on both sides. So it can be eliminated from our search. So the brute force algorithm really just iterates through all those lines, does that calculation on where all the rest of the points are, and picks off the lines that are on the convex hull. So what's this algorithm run in? What's this running time? For each pair of points, calculating that data set is a O(n)² algorithm. Since we then have to iterate through all the points again for each one of those lines, which is another O⁴ calculation, the total running time of this algorithm is O(n)³. We can definitely do better than that. So another relatively simple algorithm that has a huge performance boost over brute force is called the gift wrapping algorithm, or the Jarvis March. First, we need to find just one point that's on the convex hull. And this can easily be done by scanning through all the points and just finding the leftmost point. Next, we're going to calculate the polar angles of all the remaining points with respect to this point that we found on the convex hull and that vertical line. Mathematical properties show that the line with the greatest and least polar angle point to points that are both on the convex hull. We're just going to pick one of those and continue on our calculation. So now we have a new point and a new line. We can calculate all the polar angles again. Again, take the one at one extreme and find another point on the convex hull. We can repeat this process for each point on the convex hull, basically wrapping around all the data points to find that polygon. Yay, we did it. So how much more improvement do we get with this algorithm than the brute force approach? So finding that first edge is an order n operation. Calculating the polar angles is also an order n operation. Since we have to repeat that calculation for each point on the convex hull, the total running time is O(n) times h, where h is the number of points on the hull. That means in the worst case scenario, where every single one of the points is on the convex hull, this is a O⁴. For very complex hulls where the number of points on the hull is known to be large, there is an even more advanced algorithm called gram scan that I won't get into. But it runs in O n log n. Additionally, there have been at least 8 different algorithms that have been discovered in the last 30 years that solve this problem in O n log h. So the most appropriate algorithm for any particular convex hull problem, or really any problem at all, depends on the expectations of the data set, as well as the outright expense and maintainability of the algorithm itself. These faster algorithms might not be worth their larger implementation cost. So when you're building the code out for the first time, if you can isolate, you know that an algorithm, you may want to upgrade that algorithm later on. You can build it in such a way that that is a component that can easily be swapped out for a different algorithm later on if you do run into scaling problems. The field of computer science strives to continue finding more and more efficient algorithms to solve common problems, and also to find ways to solve new problems using our existing set of algorithms. Whether or not you consider yourself a scientist, the code that you write and the tools that you build can be used to further our knowledge of computing. It is a common idiom within the Ruby community that we love Ruby because of its expressiveness and its beauty. This sentiment comes from our artistic selves. Our programming language can be seen as our artistic medium, and Ruby as a medium is both flexible, powerful, and enjoyable to use. We talk about the beauty of code the way we talk about the beauty of a painting. The structure of the different components, the skill and artistry of our methods, and classes and modules, and the oppressive feeling when you step back and watch it all come together to form a larger whole. If Ruby is our medium, then our specific syntax choices, our method structure, our coding guidelines, that's our artistic style. There are Rubyists that subscribe to a minimalist style, and those that prefer to decorate their code with qualifiers to make their intentions explicitly clear. Ruby pushes forward an object-oriented style rather aggressively, but also allows for a functional approach. Our style becomes an identifying trait. Unlike many other artistic endeavors, it is almost assured that we will not be working in a vacuum. Programming is by definition a social activity. We write software on teams, and the software that we write depends heavily on expansive networks of projects, libraries, tools, and frameworks. As artists, we must learn to determine how our artistic style hinders or helps the teams that we work on. We create coding style guidelines for a reason. It is incredibly difficult to create a finished piece with a variety of divergent styles. Does this mean that as a community, we should all just coalesce down to a single style? You know, pick it and be done with it. That would be about as exciting as a museum with the same painting repeated over and over again on the wall. We are benefited by the ability to solve problems in many different ways, by thinking about the issue from different angles, and by implementing different algorithms. We should celebrate the differences that make us unique, to encourage our community of Rubyists to be free to try new things, to solve new problems. We should encourage the explorer that travels down the unknown path. You never know what beauty they might bring back for you. And do not make the mistake in thinking that something complex is not also simple. Complex problems require complex solutions, but each part should be the simplest thing that fits that role. Art is about simplicity. And we think of code in the same way. We espouse dry code. We rejoice in the single responsibility principle. We package up code into libraries and frameworks. This is simplicity. The best code is no code. The best code is code that already exists. The best code is simple code. To become a master craftsman, it takes time, practice, and skill. This was codified with the idea of the apprentice, journeyman, and master designations. Theoretically, anyone with enough practice could climb these ranks. If we are craftspeople or artisans, this might shake some of our previous assumptions surrounding the innate intelligence and capability. Instead, we should think of programming as a set of complex skills that take years to master, but with enough practice, anyone is capable. I think it's fitting that the first computer was actually a loom, and it was used to create even more beautiful fabrics. I am a knitter. I've gotten to the point where I feel extremely confident with a wide variety of different knitting-related skills. I've enjoyed mastering dozens of different advanced techniques. But even with all this previous experience, when I'm learning a new technique, I'm starting over as a beginner again. Yes, my previous experience makes it easier for me to read the instructions, and my built-up muscle memory makes it easier to practice the new stitches. But many times my previous experience does not map entirely onto the new skill set. And this is the glory, right? The ability to continue learning and growing, even in an area where we feel mastery. Knitting is just knit stitches and purl stitches, just like computing is just ones and zeros. Okay, great. Knitting and purling, but how do I start? There are how many different cast-on methods? Pretty soon you're knee-deep in technical jargon. What do you mean, swap these stitches with those stitches over there? How exactly am I supposed to be creating stitches? What do you mean, that makes the little lacy holes too? But once you figure it out, you can make some pretty cool stuff. And then you learn about steeking, and all of a sudden it's, what do you mean I have to cut my knitting? This is sort of how I felt when I learned functional programming, by the way. Initially, all knitters start out only being able to follow the instructions as written, which, by the way, is another thing that I think knitters do a really great job of, which is providing instructions in multiple different formats. They have written instructions for the verbal folks. They have charts for the visual. And then there's copious amounts of YouTube videos for when you really need someone to show you how to do a particular technique, and you need to watch the video over and over again 17 times in slow motion. In many ways, by following these directions, running these algorithms means that you yourself are the computer running the program Make Sweater. And if you follow the directions exactly, at the end, you will in fact have a sweater. Eventually, some people feel the need to fiddle underneath with how all the different moving parts work. Since you are here at this conference, I have a feeling that you are one of these people. Maybe your proportions, or the proportions of the lucky person you're knitting for, are a little bit different than average. Perhaps you have a particular cast-on or cast-off method that you prefer. Maybe you want to swap out the design of one of the subcomponents. Once you have mastered various algorithms and sub-algorithms, it becomes enticing to try swapping things around and seeing what you get, trying to improve the aesthetics or the performance. Now you are the algorithm creator, not just the computer. Even though I'm a knitter, sometimes knitting is not the right tool for the job. I'm not usually a fan of crocheting, but when crochet is the right tool for the job, you can't really argue with that. If a sweater needs more support in the shoulders or at the collar, Crochet. If you want to alter a garment, add a decorative hem after it's finished. Crochet. Or maybe embroidery. It's my craft. I can choose the best tool for the job. And by exploring other crafts and the benefits that they provide, my end product will almost always be improved. Craft can be a profession, or increasingly in our society, it can be a hobby. I find it interesting that we programmers also have a tendency to take our work home with us. We create silly things to go alongside our serious endeavors. We create things just to bring happiness to other people. And I don't think this is a coincidence. Getting paid for our time is nice, but at the end of the day, we write code to enrich our own lives and the lives of others. We create things for the satisfaction of a task well done, of building something functional, whimsical, efficient, and beautiful. When I was a child, I was perhaps a bit of a know-it-all. A voracious reader, I loved learning and remembering all sorts of facts from many different disciplines. And I was not shy about letting you know when you were in fact wrong. I was that kid that corrected tour guides. I loved being able to show off my knowledge, and I thought that everyone else would be as happy as I was to learn new things. But there is a difference between being correct and being right. It took me many further years of awkward social development to realize that it isn't simply a matter of knowing the correct things and remembering all the correct answers. The daily interaction that we have with our peers, providing and gathering information, forming social bonds, none of these activities rely on knowing the correct answer. And sometimes a relentless drive to find accuracy can actually hamper the formation of our friendships and relationships. If programming is a science, then we should always be looking to expand our collective knowledge, and we should be excited when others make discoveries or improvements. Diverging when solving a problem is a good thing. Exploring multiple paths, collecting information, and then bringing it all back together at the end to pull the best parts out of both sides and move forward together. That's what moves us forward. If programming is art, then we should admit that there are many right answers and accept that others have a different style. Even if we don't like them, they are still right. Rather than being divisive, this adds beauty and interest to our community. This makes our community welcoming to anyone, no matter what their style. And if programming is a craft, then we should know that the particular tools that we choose are irrelevant to our existence as craftspeople. Yet in many ways, this drives our thinking and our final result. The way we solve problems as Rubyists is going to be different than if we were using Java or C or Python. Even the differences between Rails and Sinatra or Node. We can learn from other languages and frameworks. We can take the advantage of the benefits that they provide when they're the right tool for the job. If our community continues to keep these things in mind when writing code and interacting with others that write code, then everyone's experiences will be improved. All of us are here today because we already know how to wrangle computers. Let's make sure that we are practicing the skills of empathy and communication. Continue to help others enter our community and further their own skills. What's almost as good as finding out that someone already wrote the code that you need right now? Mentoring and encouraging someone else so that in the future you can use the code that they wrote that you then need. tech is not a zero-sum game. And let's build our future together. I'd like to give a great round of thanks to Ben and Karen for running a great conference. I'd also like to shout out to Eric, Jenna, and Jen for providing me with some awesome pictures, especially since the knitting community is super into having all right reserves on all their photos. So thanks, Jenna. About half of those pictures were hers. And I'd like to thank the Esri PDX team for being a great place to work and letting me avoid doing a lot of work the last week so I could prepare for this talk. Thanks.